Hello and welcome back. Today I want to talk about coils and filters and strange noises. I want to tell you about an issue I had with my reception rig that I tried to fix using a passband filter. That filter, of course, needed to be designed, built and tested. So if you're curious about the filter's performance as well as how it helped with the noise issue, then keep watching. Now, I've been playing around lately with FT8, and sometimes the waterfall looks normal, there are various stations transmitting, regular activity, but other times, well, the band is just swamped with noise. There are some huge peaks appearing. Some bands are worse than others, but in general, this makes reception almost impossible, though transmitting still works the same. After scouring the internet to see what other users of the same transceiver experienced, if anybody else was having similar issues, one thing stood out. The receiver has an input passband of 0.55 to 30 MHz. Therefore, certain users did report commercial broadcast overdriving the input and therefore leading to interference issues, mainly coming from the AM band. So the natural solution to this is to use a broadcast interference filter, commonly a high-pass filter. Now, in all fairness, the issue I was having did not look either like AM or FM broadcast. It's a continuous, non-varying signal, so I thought maybe it's coming from some other broadcast or equipment. Maybe the antennas and transmission equipment that is all over the city, similar one is on top of my building, maybe that might be generating some noise in the HF bands, maybe from its internal power supplies or something. So that was my initial assessment. Therefore, I decided to build a bandpass filter to pass only the range in which the loop antenna works, the 20 to 10 meter band range. How hard can that be? Now, to design it, I used the LC filter design tool from Marquee Microwave, and I find this tool quite excellent because it offers a wide range of filter responses and filter types, as well as all the other options it has, like being able to select between components with exact or standard values, and you can also adjust the Q factor of the component so to make it as realistic as possible. But anyway, after playing around with it a bit, this is the filter I came up with. So it's a third order Chebyshev type of bandpass that has its corner frequencies at 12 and 30 MHz, and this should keep the component count quite low, so there's only 6 components in here, and we still get a pretty decent response, so very good attenuation both at low frequencies as well as high. So this is what I'll attempt to build today. Before building, it's important to consider that most RF filters for the HF band are made with the same types of components, capacitors and inductors. For the capacitor, it's usually simple. For small values, you just use ceramics, class 1 dielectric C0Gs. There are other better types of capacitors, of course, but these are the most common and the most cheap. For the inductors, it's a bit different. While you can of course buy them, you can also make them yourself. And you can actually DIY a set of components with competitive parameters. So that's what I decided to do. When talking about RF inductors, specifically something to be used in a filter, there are a few principles that need to be followed to get the best results. To better understand these, let's first highlight the equivalent model of an inductor. So you have of course the inductance, this is the useful bit, but you also have some resistance in series and you have capacitance in parallel. So first thing to consider is the inductance. Whatever the needed value may be, an important aspect is that this value needs to be stable. One of the easiest ways of achieving this is by using an error core, since the most significant element that affects the stability of most inductors is the variation of the parameters of the magnetic core when that is used. Now, on the subject of stability, the other aspect to consider is the inductor's behavior over frequency. The common response shape is a flat line, which at some point shoots up and then down. This transition occurs at the self-resonant frequency. After this point, the inductor starts to behave like a capacitor. The exact frequency at which this resonance occurs is calculated using the parallel capacitance. and well, the stable inductance is maintained up to about a decade below the resonance frequency. In other words, a good inductor has a high self-resonant frequency and in turn low parallel capacitance. This is normally obtained by using a single layer of turns and spreading the turns out since this capacitance occurs in between the turns. Lastly, a good inductor is considered to have a high Q factor, which is a different way of saying that it has low series resistance. Now this is mainly coming from the wire again, so there are a few strategies that can be used here. On the one hand, you can strive for a shorter wire. This can be obtained either by using a magnetic core, but this impacts stability though, or you can go for a multi-layer design, but this greatly impacts capacitance. So usually this only works for low frequency inductors. Finally, you can use thicker wire, which to be fair will have an impact on capacitance, but this is minimized the more you spread out the turns. So inductor design will always be a compromise based on how the two main parasitics, the resistance and capacitance, can be tolerated. There is no unique solution to an inductor's design, so you'll just have to balance out these parameters. For today's build, I decided to go with a classical approach, a single layer inductor with turns spread out and using thick but not very thick wire. While this approach is well understood and commonly used, you can still run into some issues. So starting from the inductance calculated in the previous tool, I used this coil inductance calculator tool, and here I just set single layer type of coil, set the units to centimeters, so it's quite important to not mix these up. So after playing around with the parameters a bit, I settled with this set of dimensions, so a 7-turn coil, 1.5 centimeter in diameter, 2 centimeters in length, and this should give a inductance of around 406 nanohenries. So I made a basic case model for this and printed it and built the coil on this. Now after adding in the wire and stripping off the ends to make it measurable, I fired up the inductance meter, and after inserting the coil, well, it's not really 400 nanohenries. It's about 530. That's more than 20% off. So we must be missing something. Now, there are 3 important things at play here. First, the calculator considers the coil's diameter to be running from one wire center to the other center. If you put your coil on a support, the diameter of the support has to be smaller. Namely, it should be the target diameter minus the wire thickness. And you can also consider a small air gap, since with thick wires, you can end up with the wire not fully touching the support. The second thing to consider is that the calculation strictly refers to the coil. Once you connect this to something, like the LCR meter, well, you need leads to perform the interconnection. And especially with very small value inductors, these leads will be able to create a significantly large loop to impact the total inductance. So your inductor should target a slightly lower value than you actually need. Anyway, after countless prototypes, I was able to fine-tune the dimensions and turns count to get the proper values I needed. So these are the dimensions I used for the final build. Now, I was not very sure of how well the circuit would work, so before going for a proper board, I tried building the filter on a perf board, and used some copper tape to make wide, low-loss traces. So all of the large components, the connectors and inductors, are placed on one side, and the small SMD ceramics on the other. An important thing to mention here is that the coils are placed at right angles, one in reference to the other, and this is deliberately done to minimize coupling in between them. So this was not an artistic choice, but rather a technical one. This practice is quite common in various devices, like this CB radio. To verify the filter's performance, I connected the 2 ports of the VNA to the filter and performed a S21 measurement. So there are 2 main things to look at. First, the general filter response. It's bandpass behavior. So we can check the 2 corner frequencies, so where the gain passes through -3 decibels, and these occur at around 10 MHz and 34 MHz. So this is more or less in line with what the filter calculator tool predicted. Now, the other thing to observe is what happens in the stop band. So do we actually get an ever-increasing amount of attenuation, like we should be? So if the components keep their properties, this line will be straight. But if the parasitics start to take over, then the line will flatten out or even go the other way. Now, in our case, at least in the analyzed range, so from 100 kHz up to 200 MHz, the filter is behaving quite well. We are getting pretty good values of attenuation on the low frequency side, so we are getting a very nice straight line up until the point where the measurement equipment hits the noise floor. So this line probably extends further, but we just can't measure it. And then in the upper frequency range, the attenuation nicely increases up until this red marker at 100 MHz, so 97, after which the amount of attenuation slightly decreases, so up until the green marker at 150 MHz, and then the parasitics take over, so signal starts passing through the filter. But anyway, if there are extreme out-of-band signals appearing on the antenna, this filter should take care of it, both on the AM band side as well as in the FM band. Now, the second important thing to look at is the passband region of the filter. So for this, I zoomed in quite a bit. I'm using 0.2 decibels per division to get a clearer result, and we can observe that the filter has quite a decent insertion loss. So there's a bit of a ripple in it because of the Chebyshev type of response, but the insertion loss is in the 0.2-0.3 decibel range, starting from about 12 MHz up to about 28-29. So you could probably get better results with a thicker wire, but for my QRP rig, this should be good enough for now. So, did it work? Well, the antenna without the filter is still noisy, no change there. And if we now connect the filter, so just put it in line on the input of the transceiver, well, it looks exactly the same. No difference whatsoever. Am I missing something? Now, in fairness, the filter is working just fine. It's doing exactly what it was designed to do. We checked it with the VNA after all. The issue here is not the out-of-band emissions which are overdriving the input, the issue is inside of the band. So this sort of filtering won't really help. What did help, however, was a simple but highly effective change. The noisy waterfall only occurred when the radio was being connected to my main PC. So a large full tower PC with dual monitors. When the same radio, same antenna was connected to the laptop, all the noise disappeared. When I left the setup on the laptop and turned on the PC, well, the noise reappeared. So yeah, this was not a lack of filtering issue, but rather noise from nearby electronics issue. You learn something every day. In the end, while the issue was solved without the use of the filter, the process of designing and building inductors is still quite an interesting and useful one. Using homemade inductors is common when working on RF circuits. You will find quite often that building an inductor from scratch can give very good results, but only if enough care is given to the parasitics and the construction. So, with that said, hope you enjoyed this video, and if so, there are more similar videos on my channel that you might want to check out. And if you want to be up to date with my latest releases, also consider subscribing. See you next time. Bye bye.